Again, welcome everyone to the STEM student talk of the 6th Polygent Symposium of Rising Scholars. My name is Clara, and I'm a PhD candidate at the University of California, Riverside, and I will be moderating today's talk. The goal of the symposium is to celebrate and showcase the hard work of our Polygent scholars, all of whom have tirelessly worked on their projects over the past couple months. We have two student presenters presenting on a variety of topics today. A fellow Polygent's mentor will be scoring each student's presentation, which will help us determine prize winners after the event. Please type your questions into the chat if you have any for each speaker, and we will allot 2 minutes for questions after each presentation. Today's speakers are Anika Ranjan and Diana Martynova. So we will start with Anika.
Hello, my name is Anika, and today my project is the future possibilities of the use of CRISPR on three eye disorders. So first, I wanted to talk about CRISPR as a background. So CRISPR is a relatively new technology that allows researchers to change one's DNA, and this can be done through embryonic editing in unborn cells or embryos, and somatic editing in living cells. Researchers create a guide RNA or gRNA sequence that binds to a target location of DNA on the genome. The Cas9 enzyme is then directed to cut an undesirable section of the genome, and it inserts a human-made guide RNA in the cut DNA. It's also important to note that CRISPR has a base capacity of 20, which means that it can take 20 base pairs at a time. So on the three diseases that I focused on, here's some background information. X-linked congenital night blindness, snowflake videoretinal degeneration, and cataract microcornea syndrome are the three genetic diseases which have the mutations which have the genes CACNA1F, KCNJ13, and ABCA3 respectively. I focused on mutations on all these three genes. My goal was to pinpoint locations that CRISPR could be used to create a significant impact, and I also chose to use CRISPR because it was affordable and its ability to insert, delete, and substitute base pairs easily. The first disease that I focused on was X-linked congenital stationary night blindness, better known as X-linked congenital night blindness. X-linked congenital night blindness is a recessive disorder which is characterized by mutations in the retina, which help to detect light and color. CACNA1F is responsible for encoding a retina-specific voltage-gated L-type calcium channel in the A1 subunit. This functions as a pore and voltage sensor and can be a top contender for CRISPR. One of the mutations was an ATG transition, which was predicted to cause the loss of a splice site mutation, which resulted in the loss of exon 41. The ATG transition would be one base pair in length, so CRISPR could be used to fix X-linked congenital stationary night blindness. The second disease that I focused on was cataract microcornea syndrome, CCMC, which is characterized by a corneal diameter of below 10 millimeters in both eyes and inherited cataracts. The gene ABCA3 is a major cause for CCMC and spans over 80,000 nucleotides long. It has a couple of missense mutations and a couple of splice site mutations. Some of the missense mutations being 115 C to G transition, 277 G to A transition, 4393 G to A transition, and 2408 C to T transitions. The splice site mutations were 4053 plus 2 T to C transition and 2765 minus 1 G to T transition. ABCA3 has multiple missense mutations and 2 splice mutations, and CRISPR could be used to fix both of these in the ABCA3 gene. However, it's also important to note that the ABCA3 gene is just newly found and hasn't had much research done on it. So CRISPR could not be potentially used to solve it later on if more research is provided. The last disease that I focused on was snowflake videoretinal degeneration, which is characterized by filial degeneration of the vitreous humor, early onset cataract, and minute deposits, among others. A mutation in the KCNJ13 gene is the cause for SVD, and it has an R162W mutation, which is an interest for us. The KCNJ13 gene mutation was a result of a C to GG codon changing into a U to GG codon. This results in the arginine amino acid being changed into a tryptophan amino acid. Tryptophan is a stop codon that results in a nonsense mutation, leading to the production of the R162W mutant. CRISPR would be able to insert and substitute the U base pair, changing it into a C, resulting in a potential fix of the disease. However, there are some limitations to keep in mind. The first of all is that while it is relatively cheap and easy to use, there are a couple limitations like the base pair, which is 20, and also off-target effects. Off-target effects are unintentional mutations effects caused by the guide RNA and can lead to more mutations later on in other parts of the DNA. Ethical questions can also be raised mainly from embryonic editing, which is editing done in the embryos. Overall, all three diseases can be used to be fixed with CRISPR, but there is something to consider that ABCA3 gene in CCMC hasn't been fully researched. So it's possible that CRISPR might not be able to work with more research done on that gene later on. But however, for the other two diseases, CRISPR would be able to make a profound improvement in one's health. Thank you.
Great job, Anika. And if anyone has any questions, you can either unmute yourself or you can put them in the chat. I have a question while we're waiting. What was the most exciting part of this research for you?
I think the most exciting part of this research was, I would say there were a couple of things. First thing was just learning about the disorders in general and understanding how they work and what genes are impacted by them. And the second part was researching CRISPR and seeing how CRISPR works more in detail, and also making that connection between the diseases and CRISPR and seeing which ones could be potentially solved. It's interesting.
Yeah, that's really awesome stuff. Have you thought at all about the ethical implications of research in CRISPR?
Yes, in my personal belief, I believe that CRISPR should be used if people are willing to spend that much money, because CRISPR is, while it is more affordable, it is kind of still inexpensive in today's standards. But also, ethically, if someone knows all the ethical damage that it can do, all the damage it can do, potential damage it can do in one's health, but is willing to take that risk, then I believe it's okay. I do believe that there needs to be some set guidelines on embryonic research, and I believe that somatic research would be fine to do, again, with the permission. Embryonic research, unfortunately, has already been done in some countries, which I believe should not be allowed.
Really great answer. All right, any other questions? I'll give it a couple of minutes, a couple of seconds. All right, well, let's move on. Next up, we have Diana Martynova.
Hello. So my topic is novel data-driven sepsis diagnosis using biomarkers by Diana Martynova. And our research question is, how can AI process lactate levels, C-reactive protein levels, and interleukin-6 levels to diagnose sepsis? So every 1.7 million people every year are diagnosed with sepsis in the US, and it's a bacterial infection that leads to death in roughly 250,000 patients. It's one of the leading deaths in the US and one of the most common deaths in hospital as well. So sepsis is hard to diagnose because it requires multiple tests to fully diagnose it, because its symptoms, such as shortness of breath, fever, high heart rate, discolored skin, and dizziness, are very similar to many other diseases. A survey of more than 1,000 hospitals stated that 86% of intensive care specialists misattributed the systems, while 45 missed the diagnosis completely. So in this project, we will be creating an AI program to, when given the patient's lactate levels, interleukin-6 levels, and C-reactive protein levels, as well as symptoms, will be able to identify whether the patient has sepsis or not. And so this program will assist the doctor by minimizing the number of tests as well as time to finalize the diagnosis. Our objectives is, can we use these 3 biomarkers to identify sepsis? How accurate can we make this program? And will this program be able to diagnose faster than a doctor? And our hypothesis is that the AI will actually be able to use interleukin-6 lactate and C-reactive protein levels to diagnose sepsis faster and more accurately than a doctor diagnosing sepsis. The doctor should just do a simple symptom check of temperature, blood pressure, and heart rate, input this into the program, and then the doctor will perform tests for suggested combination of biomarkers, which he will then input into the program, which will then give the probability of sepsis, as well as the next steps to refine the diagnosis. And I'd like you guys to keep in mind that this program is meant to assist the doctor, not fully replace a doctor. So we will begin by gathering data from PubMed, Mimic, and GitHub related to these 3 specific biomarkers. And AI algorithms usually perform best as an optimization problems. So the sepsis diagnosis will be the maximization problem, and the probability of the patient survival will need to be maximized in this case. We will then train the program using the collected data and test the accuracy. So the process of sepsis diagnosis consists of multiple steps where decisions need to be made under uncertainty. And we leverage reinforcement learning research, which was successfully applied to many old games. And this is why to the AI, we present the sepsis diagnosis as a game, therefore naming the program the game of sepsis. And at each point of this game, the AI, based on the available data, has to make one of these 3 possible decisions: either confirm sepsis, rule sepsis out, or suggest the most efficient biomarker blood test and then wait for its result. And so the game is over either when sepsis is confirmed or ruled out. And again, the objective of the game is to maximize the probability of the patient's survival, which will be given as a reward to the program. So a correct diagnosis is necessary, but not sufficient. The survival of the patient also depends on the time spent in diagnostics, and biomarker tests take different times. So we need to somehow convey this to the AI. So then the biomarker tests are assigned different penalty values, which are subtracted from the N reward. And these penalty values cannot be too low, or else the program would just ask for all biomarkers, which is unnecessary and takes too much time. And on the other hand, they shouldn't be too high, or else they will discourage the AI from using any biomarker tests and just guess. And so we performed a series of experiments to choose the penalty structure under the diagnosis is both reliable and takes the least number of tests. So for IL-6, the days on average is 3, and the sensitivity is around 85%. Therefore, we gave it a point value of 1.2, which is the sensitivity multiplied by the number of days. We use the same function for the other biomarkers to create the best point value. So this program is based on the open source RLZoo framework by OpenAI, and it was trained and tested on data from Mimic4, which is a large public data set on hospitalizations. Mimic4 data was very limited on CRP and IL-6, and we overcame this problem by pulling out data from recent papers and then finding an overall distribution of the values in the biomarkers. The program also used a deep Q-learning algorithm. So each training episode started with providing basic symptoms and then continued by asking for more tests until a diagnosis is made. And overall, our program was able to diagnose a patient in around 2 steps, meaning it would ask for only 1 biomarker. The program also had an 84% accuracy for diagnosing a patient correctly, compared to a doctor who uses 3 biomarkers on average and only achieves a 63% accuracy. Here is our results in a graph. Again, it takes a doctor a few days on average to fully diagnose a patient, so around 48 hours or 2 days, and our program takes around 24 hours or 1 day. And our program overall works fast. It takes 1 day to get the results back for all the biomarkers to fully refine a diagnosis. So in the future, we need a better clinical data set with more biomarker data since we were very limited on CRP and IL-6 values. The program should also be able to use more biomarkers for sepsis since it's currently only limited to 3 when there are many others. The program needs a user interface which can be easily used by doctors, and the game of sepsis can be expanded to diagnose other diseases as well. Here are my references. Thank you for listening.
Great job, Diana. That was super interesting. So any questions, again, can be put into the chat. So my understanding of sepsis is that it is life-threatening and can be so quickly after exposure. Is this going to help in a way, if it's going to help increase the rate at which we diagnose sepsis, what are the implications for human health and, I guess, survival rates?
So basically, yeah, sepsis, it can precede to septic shock, which is multiple organ failures from this bacterial infection in around 24 hours. Meaning in these 24 hours, these three biomarker levels will either go up or down. And this is when we need to test the patient in order to get the optimal values and to quickly diagnose the patient faster. And this is basically the main goal of the program, because doctors usually miss the diagnosis of sepsis completely because it is just very hard to interpret from the beginning, since symptoms are very similar to like the flu, for example, or the cold. And so with this program, the doctor will have an option to quickly and easily diagnose the patient. So that they'd have the option of knowing that if the patient does indeed have sepsis, we can use this program to diagnose it faster.
Yeah, so very, very important implications of this research. That's great. Do you know, this is just a random question, do you know the most common cause of sepsis? Because I know I have 3 cats, and I know that cat bites and cat scratches can cause sepsis.
No, I don't initially know the main cause of sepsis. I just know it's an infection that finds its way into your bloodstream. And then from there, it can lead to organ failures.
Well, great work to both of you. Do you have any questions for me? No? All right. You're free to stick around if you like. I'm going to keep this going for a little bit longer. But other than that, very, very great work, and we're very proud of you, and thank you for presenting at the 6th Annual Polygenic Symposium.
Thank you.